want us to talk about one important concept. I think we'll be writing up shortly. One important concept is energy. So we'll talk about peak sun hour. So the following equation provide a quick and simple way to estimate energy yield of a PV plant over a particular period of time. Now, one important concept I would like us to talk about is peak sun hour. This is PSH, peak sun hour. Okay. Now, peak sun hour is, you remember when I talked about standard test condition, and I told that the standard test condition of a solar panel is 1,000 watts per meter square. That is the standard test condition. But when the sun comes out, it is not at one, it can be at 200 watts per meter square. It can be at 400 watts per meter square. Even at peak, it can be at 800 watts per meter square. So it actually does not get to 1,000. In some cases, sometimes it might get to 1,000 watts per meter square, right? Now, and the sun comes out in the morning, it goes and it peaks around afternoon, around noon time, and then by evening, it begins to drop, right? Okay, let me use this. I'll go back to another example. Let me use this to explain it. So let me just explain what the peak sun hour means, because it kind of creates some level of controversies anytime I bring this up. I was in one of the class and I said that if you're doing your design, you should consider a peak sun hour of 4 or 5. And somebody said, no, that the sun comes out in the morning and it stays till around 4 or 5 in the evening. It cannot be 4 or 5 hours. I said, okay, that's not what I mean. Now let us look at standard test conditions, okay? When you go to the market, I think this also has to come to the question that one of our colleagues asked, where you said, if you go to the market, you see a solar panel that is rated 300 watts. Why is it rated 300 watts? Okay, so there's what we call standard test conditions. And these standard test conditions are the conditions upon which these models are giving their ratings. Okay, now there are about 3 items that we're going to talk about. So due to the variability of power output of PV cells, depending on parameters such as irradiation, temperature, that we've talked about this already, and the performance of different cells operating under different conditions, they cannot be compared easily. If you have a certain solar panel installed in Germany and you have another panel installed in Nigeria, you might not be able to compare them because their operating conditions vary. The temperature, the irradiance, they are all different. So you might not be able to compare them, you know. So if that is the case, then at what condition is the solar panel, at what condition are they giving their ratings? So in order to enable meaningful comparison between PV cells or PV modules, the rated output of this of the cells or modules is always measured under specific conditions. So these conditions are standardized across all testing facilities across the world and are called standard test conditions. Now, there are about 3 items. One of them is the light spectrum, or the AM. The AM is like air mass or light spectrum, it's 1.5. And then you have the irradiance. So the solar panels are tested at 1,000 watts per meter square. That is the standard test condition before they can be said, okay, this is 300 watt solar panel. And there's also a temperature. So let us look at the physical aspect of a PV system. Now we're coming back to the PV system because it's at the foundation of the PV module. So the electrical power P for DC system measured in watts. We already know that in our first introduction we talked about power, and I know we learned about this formula where we said that power is equal to voltage times current, and of course times power factor if you're now considering the load. Okay, so power is equal to voltage times current, whether it is direct current or alternating current, it's the same, right? So that's how power is measured. So the power is a product of voltage and current. Now, how does this work on the PV level? Now, under normal sunlight condition, PV cells voltage remains fairly constant. However, the cell's current is very sensitive to sunlight. Higher solar irradiation will produce a higher electrical current. Low solar irradiation will produce a low electrical current. So what this simply is saying that once the sun comes out, the voltage of your PV module is relatively constant. It does not change so much. As long as the sun comes out, it does not change so much. But what actually changes so much is your current. Remember that power is a product of voltage and current. So when the sun comes out, the voltage is almost, relatively stable, but this current changes so much. If the sun increases, the current increases. So essentially what this is saying now, what is the voltage of the solar panel when the temperature drops from 25 degrees centigrade to minus 10 degrees centigrade? What is going to be the maximum power point voltage? That is just the question. And the same thing goes for the next question. What will be the minimum open cycle voltage? Now, the minimum is going to be when the temperature is highest. You remember here we did for minus 10. So in this case now, it's going to be when the temperature is highest, which is what's the highest temperature there? 70. Based on the question that the data that we had, the highest temperature was 70, no, not 70, 45. The highest temperature that we had was 45, right? But again, 45 is the temperature of, the temperature of the module, right? But in this case now, we have to account for the standard test temperature. So what this means that the temperature was already 25, then it now has to move now to another 45, right? So in that case, you're going to have 45 plus 25. That's how we got 70 degrees here. I think that's so the minimum open circuit voltage will be produced at the highest ambient temperature of 45 degrees centigrade, but the cell temperature of rooftop or open field PV system can be 25 degrees centigrade higher than the ambient temperature.